Good day, everyone. So we will be reviewing the last part of Chapter 3 of Wetzel's Limnology textbook, edition number 4, and we'll be focusing on water's interface properties, which are surface tension and refractive index. And beforehand, we reviewed the thermodynamic properties of water, and the last thermodynamic property of water that we reviewed was electrical conductivity. But before we go into that section, let's look at those two graphs that are mapped in figure 3-3. So on the left, we are mapping water temperature with electrical conductivity and salinity. So, for example, the purple line maps waters with a salinity of 35 grams per kilogram, where here in the lower part of the graph, we are mapping air-saturated water. And then here we are mapping in blue, we are mapping the water with a salinity of 0.1 gram per kilogram. But the point overall of this graph is that electrical conductivity increases with water temperature. And more specifically, electrical conductivity is higher for waters that are saline compared to water that are pure and that have low salinity. On the right, we are mapping the refractive index with water temperature. So there as well, as we're moving from left to right, we are increasing water temperature. On the y-axis here, we have the refractive index. So as you are moving up the y-axis, you are increasing the refractive index. And then on the right, we're mapping the critical angle. And so in this case, as you are moving down the y-axis, we are increasing the critical angle. So here also what we're mapping is we're mapping the property of the refractive index, which is a measure of the speed of light in a substance, but also we are focusing on very specific wavelength. So this is pure water at a wavelength of 400. This is pure water at a wavelength of 550. This is pure water at a wavelength of 700. And then this is saline water at 35 grams per kilogram at a wavelength of 550. So in all cases, as water temperature increases, we have a decrease in the refractive index N. However, we have an increase in the critical angle. So we have somewhat of this inverse relationship between water temperature and the refractive index or the critical angle. So let's jump right in and kind of find out why that is. So the first thing is surface tension. So the intermolecular hydrogen bonding in water, balanced in all directions, is interrupted at the water's surface. Water molecules at the surface are then subject to an unbalanced force directed inward toward other water molecules, which increases the internal pressure, and also directed sideways as surface tension, acting to reduce the surface area. The surface tension at the air-water interface, or pure water, is higher than that for any other liquid except mercury. It decreases with increasing temperature and increases slightly with salinity. The restoring force from this strong surface tension is the cause of centimeter-scale capillary waves on the water surface. It also quickly damps these waves when the forces that cause them die down. Generation of capillary waves by localized wind gusts roughens the water surface, making the location of these gusts visible as darker cat paws. It also provides a mechanism for estimating surface wind speed from spaceborne radar systems, which are sensitive to the small wavelength of capillary waves. Surface tension is also strong enough that air bubbles of less than about 1 millimeter in diameter in water are essentially rigid spheres with pressures higher than ambient inside them. In contrast, larger bubbles have more complex and even time-varying shapes that affect their rise rates in complicated ways. Since the pressure inside bubbles generated by breaking surface wave is larger than ambient pressure, air-water gas transfer is enhanced and can lead to supersaturation of surface waters. Finally, laboratory studies show that the extremely high pressures within collapsing gas bubbles, less than 1 micrometer, in size in water can cause temperatures within the bubbles to exceed 10,000 Kelvin, resulting in the generation of light, a process called sonoluminescence. In relatively calm areas, a variety of organisms, collectively called neustons, which would otherwise sink, live on the surface supported by the surface tension. However, the surface tension of water can be greatly reduced by the addition of natural or anthropogenic organic compounds. Surface tensions in eutrophic lakes and bogs can be as little as 75% of the pure water values. Decreases in surface tension also decrease the capillary wave roughness, making areas with higher concentration of these substances visible as slicks when viewed at low angles. Refractive index. The refractive index is a measure of the speed of light in a substance, and it governs the change in the direction of light rays as they propagate through a surface. Refractive effects in water are responsible for many fascinating and beautiful features visible in, on, and above lakes. The most well-known of these include rainbows, the twinkling of stars, and the sun dappling of lake bottoms through the formation of caustic networks. When slanted light rays strike the water surface, some of the energy is reflected and some enters the water. On entering the water, the slanted light rays refract toward a perpendicular to the surface with angles related to the refractive index using Snell's law. Conversely, they refract away from the perpendicular as they leave. Light within water will not be transmitted back to the air if it strikes the surface at angles larger than a critical angle of about 48 degrees. Instead, it will be reflected back into the water. Refraction in water is also slightly greater at shorter wavelengths, so white light will be split up into different colors if it passes through a water interface at an angle. The refractive index of pure water is about 1.336 at 25 degrees C, and its variation with temperature and salinity is very roughly proportional to the associated density changes. A change of 1 gram per kilogram in salinity will have about the same effect on the refractive index as a 10 degrees C change in temperature. Refractometers are therefore a useful method to quickly obtain the salinity of very small quantities of waters if salinities are in the seawater range and temperatures are controlled. Refraction at the water surface makes it difficult to view the lake bottoms through a surface wave field. Conversely, strong density gradients near the surface containing many small ripples and turbulent eddies are sometimes visible to the naked eye by the blurry nature of light upwelling through the associated refractive index variations. Refractive index changes at water surfaces and or changes in density within water also allow for a variety of flow visualization technique in laboratory studies of fluid processes. In summary, for Chapter 3. Water is a unique substance with unusual properties extensively influence physical, chemical, and biological processes in freshwater ecosystems. Hydrogen bonding and the structured nature of water molecules is responsible for many of the unusual properties of water. The density of freshwater is a maximum at around 3.98 degrees C and is much greater than the density of ice. Additions of dissolved matter increase density, as does increased pressure. Density also increases when water masses mix. The heat capacity of water is far larger than that of land and air, so lake temperatures are more stable than those around them. Viscous drag governs the dynamics of small bubbles and organisms. Electrical conductivity in natural waters is largely governed by salinity, although exact relationships are somewhat dependent on the chemical composition of the dissolved salts. Surface tensions at the water's surface is high, capable of supporting an entirely separate ecosystem, but this tension can be greatly reduced by the addition of dissolved organic compounds. And lastly, the refractive index of water is responsible for many of the beautiful features seen in, on, and above lakes. Thank you, and see you next time for Chapter 4.